then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, Precalculus students. Welcome to lesson number 6. Here we go. Okay, so today we're talking about function symmetry. And so there's two types of symmetries. A function could be even or could be odd. Those are our two function symmetries. And that's what we're going to do on today's agenda. So not reviewing anything today. Today we're just going to look at even functions and odd functions. So for each, we'll give an algebraic definition and break it down. And then we'll also give a graphical representation and also explain that as well. So let's begin with even functions. So an even function, the algebraic definition is that f of negative x equals f of x. That may seem a little vague, but I'm going to explain it because that's pretty important. So the algebraic definition is that f of negative x equals f of x. And the graphical representation is that such functions are symmetric to the y-axis. And when we look at this, when we break down the algebraic definition, you'll see why calling such functions even is such an appropriate term. Okay, so let me look at an example of an even function and kind of break it down with an algebraic definition and the graphical representation. Okay, even functions. So here's an even function. One of the simplest, most elementary even functions there are in the world today. So f of x equals x squared. That is an even function. And I can show it using the algebraic definition and also the graphical representation. Again, the algebraic definition is that f of negative x equals f of x. So if I was to plug in negative x for x, I should get the same thing. If I test it, f of negative x, that's negative x squared. So that's negative x times negative x. Well, that would simply be x squared. So in fact, anytime we raise a negative number to an even power, it becomes positive. This is why these are called even functions. From a polynomial standpoint, they have to have even exponents, meaning any function I take with even exponents, f of negative x is going to equal f of x every time. Because again, when you raise that negative x to an even power, it just turns into a positive x. So that's why we call them even functions. Now, of course, even functions go beyond polynomials. And so you have some trigonometric even functions and other type of even function. So it goes beyond polynomials. However, when looking at polynomials, which is what you tend to see the most of, really all you have to do is look at the exponents. If all of the exponents are even, then the function is going to be even. If any of the exponents, again, dealing with a polynomial function, are odd, then the function can be even. So, for instance, if you have something like f of x equals negative 3x to the fourth plus 2x squared plus x minus 8. And if I plugged in negative x, so if I found f of negative x, that's negative 3 times negative x to the fourth plus 2 times negative x squared plus negative x minus 8. And if I simplify this, again, negative x to the fourth is just x to the fourth. Negative x squared is just x squared. But this negative x here is going to stay negative x minus 8. And this is not the same as this because of this guy is different from this guy. And what messed it up is that this is raised to an odd power. This is raised to the power of 1. So again, for an even function, particularly if it's a polynomial, you just really need to see even exponents. Now let's look at it from a graphical representation because we all are familiar with how the graph of x squared looks. So f of x equals x squared. And so let's graph this guy. And so you know that the graph looks something like this. Right, so that's the graph of x squared. Maybe I could have constructed a better graph than that, but we'll live with it for now. And so when it says it's symmetric to the y-axis, this is the y-axis here, of course. What it means is you're going to have mirror images on both sides of the y-axis. So the y-axis succinctly cut the function in half, and you should have mirror images on both sides of the y-axis. I mean, if you took one half of the y-axis and reflected it over, it should give you the other half. So that's what it means to be symmetric to the y-axis. You should have mirror images on both sides of the y-axis. Now I want to graph a couple of things here. And so for this particular lesson, you are going to need to be able to graph. You may not have a calculator, so there's a calculator online you can use, no problem. So there's a lot of calculators you can use. I guess you can find online. To me, the easiest one is Desmos, so I'm going to desmos.com. And I'm going to click on graphing calculator. All right, and so I'm going to graph what we just looked at, f of x equals x squared. All right, so that's the graph of that function. And in fact, this is a parabola, so you've been taught for a very long time that the graphs of parabolas look like this. But in fact, x to any even power is going to look like this. So if I put, instead of 2, if I put a variable here, so say x to the power of a, and I define a to run from say 2, let's say 2 to 10 with a step of 2. So basically I can slide a is going to be a slider, and I can slide it from 2, 4, 6, 8, 10 like that. So here I am sliding a. So right now it's x squared. There's x to the 4th. There's x to the 6th. There's x to the 8th. There's x to the 10th. So they all look fairly the same. They all take that shape. And any even number I plug in is going to look like that. And if we just, just throw in random polynomials, it doesn't matter about the coefficients, whether they're positive, negative, even, or odd. So if I get like negative x to the 4th, and I want to do 40 minus 3x squared plus 1. And I didn't put equals there. And so again, you can see a parabola looking function. Now, when you get to higher powers and you have multiple even powers, they're not all going to look like parabolas. Sometimes they'll have little grooves in them, but you can still see this is an even function. Here's the y-axis here, and I have mirror images on both sides of the y-axis. So that's how an even function relates. So you have to be able to recognize it being even from the equation of the function, and also you have to recognize it being even from the graph. So there are some functions right now with your knowledge base, you can do this test of f of negative x equals f of x. Right now with your knowledge base, you can do that test with polynomial functions. Well, maybe some other functions, like you're unable to do that. For instance, if the function was f of x is 9 cosine x. So say f of x is 9 cosine x. Now, you may not know what happens right now if you plug in negative x into cosine x, because it's not a polynomial. So you may not understand how that trigonometric function works. So there's going to be functions where you're not going to be able to use the algebraic definition, because you don't really understand how those particular functions behave. And this would be an example of that. So for those type of problems, you're going to have to graph the function and just look at the graphical representation. So later in this course, you will understand that cosine of negative x is indeed cosine of x. So this is indeed going to be negative. Excuse me, not negative. This is indeed going to be cosine, 9 cosine x. So f of negative x is indeed equal to f of x. So this is indeed an even function, but you're not going to know that till, a little bit later in the course. So a problem that you see like this right now, you're going to have to graph it. And so what you would do, either your graphing calculator that you have, or on Desmos, you're just going to type 9 cosine x, and you're just going to take a look at the graph and see if it appears to be even. Now again, when we're looking at the graph, you want to locate the y-axis and just see if you have mirror images on both sides of the y-axis. Obviously you do here, and so when you have that, your function is an even function. Okay, let's look at odd functions. So for an odd function, the algebraic definition is that f of negative x equals negative f of x. So basically the same function, but all the signs are changed. That's what negative f of x means. And the graphical representation is that it's symmetric to the origin. It's symmetric to the point 0, 0. And that may be a little difficult to understand, so we'll give a demonstration of that to make that a little more lucid. Okay, so let's look at a very elementary example of an odd function and dissect it from these two definitions. Okay, so for even functions, I started off with the basic even function of f of x equals x squared. So for odd functions, I'm going to start off with the basic odd function of f of x equals x cubed. Now that's an odd function. Now I can do the algebraic test. If I do f of negative x, that's negative x cubed. And just as we stated, a negative number raised to an even power is always positive. A negative number raised to an odd power is always negative. So negative x to the third power is negative x cubed, which is the opposite of this. This is f of x. This is negative f of x. So that's showing as odd on the algebraic definition. So again, as for even functions, all the exponents must be even. For odd functions, all the exponents must be odd, but there's one caveat with odd functions. So it's even for polynomials, it's just not making sure that all the exponents are odd. I'll get to that momentarily, what that one caveat is. But for right now, let me look at the graph of this particular function and explain what I mean by symmetric to the origin. So the graph of this function will look something like this. Now notice, based off the definition, based off the algebraic definition, that f of negative x equals negative f of x. What that means is, if, say for instance, I have a value right here, this is not the value. Well, let's say this is the value 1, 1. So if I have 1, 1, if I have 1 for x and it gives me 1 for y, then if I plug in negative 1 for x, it should give me negative 1 for y. So that's kind of how the graph goes for odd functions. So that's what we mean by f of negative x equals negative f of x. Now, a very easy way to understand looking at a graph if it's symmetric to the origin is a simple rotational test. Meaning, look at how the graph looks right now. If this is indeed an odd function, if I rotated 180 degrees, it should look exactly the same. So look at the graph right here. I'm going to rotate this 180 degrees. And as you can see, the graph is exactly the same. Now, the key is the graph should be exactly the same. Shouldn't be similar. It should be exactly the same. For instance, I'm going to make just a random graph. No function in particular. Well, perhaps this is a particular function. So let's say this is my function. Okay, that's my function, right? And it looks tremendously similar to this graph, correct? But it's slightly different. Now, do you think this is the graph of an odd function? So right now we're only looking at the graph, so we're not looking at any particular function equation, just the graph. So we're trying to get the answer from just the graph alone. So do we think this is odd? Well, the check, of course, would be to rotate it 180 degrees. Now, is the graph the same? Hopefully your answer is no. It should be similar looking, but if you notice right here, this point is above the x-axis. This guy is above the x-axis. But when I rotate it, this guy is below the x-axis. So that's not an odd function. And the graph of this function is kind of like this. So this is kind of the function f of x equals x cubed plus 1. Right, that plus 1, you're understanding, that plus 1 is what moved this graph up 1, correct? Well, let's do the check. F of negative x would be negative x cubed plus 1. That's negative x cubed plus 1. That's not f of negative x. That's not negative f of x. Negative f of x means you change the sign of everything in the function. Negative f of x is negative x cubed minus 1. That's negative f of x. This guy is not negative f of x, so this guy is not odd. So what's the problem for this particular function? It's this constant. So for even functions, it doesn't matter because, again, what does this constant do? It just moves the graph up and down the y-axis, whether the number is positive or negative. So if I did like -5, we'll just move the graph down 5. So for even functions, since even functions are symmetric to the y-axis, being moved up and down doesn't affect them. Here is an even function. If I move this up and down the y-axis, it's still going to be symmetric to the y-axis. It doesn't change it. But for an odd function, once you move it off of the origin, and I'm not saying an odd function must go through the origin, that's not correct. But if it intersects the y-axis, it has to intersect it at the origin. But once you move it up and down, it's no longer odd. Because if I move this graph up, when I rotate it, it's going to be down. If I move this graph down, when I rotate it, it's going to be up. So if I'm looking at a polynomial for an odd function, I have to have all odd exponents and I can't have any constants. That's the difference. So for even functions, polynomials, you have to have all even functions. That's it. That's the condition. But for odd functions, polynomials, you have to have all odd exponents with no constants. You cannot have a constant for an odd polynomial function. So only odd exponents, no constants. That is the difference. Okay. So I just want to go through a few examples. We analyze the examples graphically, And algebraically, of course, there are going to be some problems that we can't analyze algebraically, and we're going to have to look at graphically. And when you do your assignment, there are going to be some problems where I give you the function equation, and there are going to be other problems where I just give you the graph. So need to be able to recognize it from both perspectives. Okay. So again, we're just doing examples. And if we can do it algebraically, we'll look at the algebra first. If not, then we'll go to the graph. So let's say our function is 36 over 4 minus x squared. 36 over 4 minus x squared. Actually, for the sake of seeing this a little bit clearer, I'm going to say 9 minus x squared. So, and the reason I'm just changed that, we'll look at the graph of this as well, and the graph will look a little clearer with that being a 9 instead of a 4. All right. So the question is this odd, even, or neither? Some functions are not odd nor even, so a function could be neither. So the question is this function odd, even, or neither? So of course, the thing we want to do, if it's something that we're able to do this with, is just find the value of f of negative x. So let's find f of negative x, which is 36 over 9 minus negative x squared. Now, the thing we can reconcile with is the fact, and this is not a polynomial function, this is a rational function. But the fact that our only x value is raised to an even power, we know that when we plug that negative x, we're going to get the exact same thing. So this is going to be 36 over 9 minus x squared. So again, we do get f of x. So this is an even function. And if we can graph it, of course. So let's say for whatever reason we couldn't figure out what f of negative x is. Okay, then our other option is to graph this function. So I'm going to go to Desmos and graph this guy. So if we graph it, we have 36 over 9 minus x squared. And there's the graph. And that's the reason I brought this. I changed this number right here to a 9. You notice how that's hidden at 4 right there. That's your y-intercept, and it just comes from the quotient of 36 divided by 9 is 4. When I had it as 4, it would have made that number 9, which wouldn't have showed a lot. So that's the reason I changed that number. But you know, if you look at it, here's the y-axis here, and this is definitely symmetric to the y-axis. You see mirror images on both sides of the y-axis. The y-axis is in the middle of this guy, and you see mirror images on both sides of the y-axis. Let's look at another example. So another example, say my function is the absolute value of x. And so I'll do the test. So I want to check if this is odd, even, or neither. I'll find f of negative x. And so this is the absolute value of negative x. Of course, the absolute value of anything just makes it positive. So the absolute value of negative x is equal to the absolute value of x. So that's the same thing. If that's difficult to understand, like the absolute value of negative 3 is equal to the absolute value of 3. So then the absolute value of negative x is equal to the absolute value of negative x. The absolute value of negative x is equal to the absolute value of x. So this is indeed an even function. I'm not going to graph this in Desmos. You guys should be familiar with this graph. It looks like a V. So the graph is like that. And obviously you can see, pardon the sloppy graph, I should have put a little more time into it, but hopefully you can see this is symmetric to the y-axis. But let's look at another problem dealing with an absolute value. So let's say f of x is the absolute value of x plus 2 minus the absolute value of x minus 2. Now for this one, the f of negative x check is not as simple because it's just not the absolute value of negative x. It would be the absolute value of negative x plus 2. That may be a little difficult to reconcile with. So this is a problem that you probably want to graph. So let's graph this guy and see what happens. And what you don't want to do, you don't want to just make the assumption, because you know that when the function is the absolute value of x, that's even, that every time you see an absolute value, the function is going to be even, because not true. Function could be odd and a function could be neither with an absolute value. But let's see what happens in this case. So I'm going to graph this guy in Desmos. And by the way, to get an absolute value in Desmos, we're going to type ABS. That represents absolute value in most languages, most computerized languages I'm speaking of. So the absolute value of x plus 2 minus ABS, absolute value of x minus 2. And there's the graph there. Now look at this graph. What do you think? So hopefully you see that this is odd. This is indeed an odd function. Just envision this being rotated 180 degrees. It's going to look exactly the same. So this is indeed an odd function. So again, don't assume just because you see absolute value that it's going to be an even function. It could be odd, and it could be neither as well. For instance, if I just did this plus 1, and this is now neither. It's not even. Obviously, it's not symmetric to the y-axis. It's not odd because it's moved up. When I rotated it, this will be down. So it's neither. Okay, let's look at another problem. So here I'm just going to type this one in versus writing it down, because this is not one. This is one you're not going to know how to do the f of negative x deal. So here is the function is going to be ln x. And so again, this is a function where you are unfamiliar with what happens when you plug in negative x. So this is one you wouldn't be able to do with an algebraic test. You would have to graph it. And so here is the graph of the absolute value. Excuse me. So here is the graph of ln x. So let's go through the checklist. Again, we're just looking at the graph. We can't do right now. You're unable to evaluate f of negative x. So let's see, is it even? Yes or no? That's a no. If this was even, this thing I see on this side of the y-axis, I would have to see a mirror image on this side of the y-axis. Meaning if this was even, you would see this action on the other side of the function. You're missing an equal sign. So this is how it would look if it was even. You would have to see the same thing on both sides of the y-axis, but obviously you don't see that, so it's not even. Is it odd? So think about rotating this 180 degrees. If you rotate this 180 degrees, would it look exactly the same? And hopefully your answer is no. So this would not look exactly the same if rotated 180 degrees. So this is neither. So this is neither odd nor even. So again, some functions are going to be neither. Okay, we're going to stop right there. And so hopefully we gave you an understanding of what an odd function looks like and what an even function looks like. And hopefully you're able to tell from either looking at the function itself or the graph of a function if a function is odd, even, or neither. And we will see you next time.